Welcome to the 2013 UWCSE Industry Affiliates Meeting. First of all, I'd like you to join me in thanking Kay Beck-Benton and the rest of the CSE staff for pulling everything together. It's a huge amount of work. It's a great pleasure to introduce Jeff Heer. Jerry Noe came here as the founding chair of Computer Science and Engineering, then the Computer Science Department, in 1968, so 45 years ago, unbelievably. And Jerry's mantra always, I remember when Hank and I first arrived, was, hire people smarter than you. Now, for me, that wasn't too hard. For Hank, it's a lot more difficult, but we've really just been on a remarkable record of recruiting great people, actually for many decades, since right after I was hired. And the past few years in data science and other areas have been extraordinary. Jeff is one of those great data science hires from 2 years ago. You heard from Carlos Gestrin here, those of you who were here last year. There are many more to hear from in future years. As I mentioned this morning, Jeff and his wife just had a baby, how long ago? 8 days ago. So he needs to be getting home. He's the only guy who got less sleep last night than I did. So let me ask you to welcome Jeff Heer.
Right. Thank you, and it's great to be here. So what I should mention is for the last 5 years, I've actually been an assistant professor of computer science at Stanford University, and I'm very happy to come here to UW where I get to trade in my cardinal for a more royal hue. So what I'd like to talk about today is our work on really helping people more effectively work with data. And so here's a nice quote to kind of give you some motivation for the type of research we do. This is from Hal Varian, Google's chief economist, who back in '09 wrote that to understand, process, extract value, visualize, and communicate data is one of the single most important skills going into the next decades, because we really do have essentially free and ubiquitous data, so the complementary scarce factor is our ability to understand that data and extract value from it. And so really the focus of our research efforts is to allow us to do that more effectively. So it's a combination of data science, databases, visualization, and at the forefront, human-computer interaction. So let's start with an example. Here's some data. This is actually a visualization of my own Facebook network from a couple years ago. And this is using a particular visualization technique to try and get a sense of patterns and structure within this particular data set. Here, people are represented by circles, and then gray lines represent edges connecting them if they have a friendship relationship. In addition, what we've done is size the circles by betweenness centrality, which is a statistic that gives us a rough sense of how central people are in the network. So for example, if I wanted to route messages, who would be good people to send it to? And here we've used a particular technique called a force-directed layout, where basically by having a physics model where nodes repel each other and edges act like springs, we then let that system settle, and then we hopefully get informative diagrams. And so take a look at this diagram and get a sense of what you see. Imagine that almost all of you immediately notice 3 pronounced clusters. So one giant blob in the center. Turns out that represents a number of researchers in my field, plus a number of people in my graduate school cohort. And then you might see these additional satellites, which turns out are different friendship circles from different parts of my life. And we might be tempted to stop here and think that we have a good sense of the overall structure of the data, but we'd be wrong. Well, this might be a useful, orienting visualization. We can get more insight if we shift our perspective. So for example, here's a different visualization technique. Here we use an adjacency matrix, which really puts the edges front and center, where before we had a big hairball, now we can see all the individual edges. In this case, the rows and columns represent people, and they're repeated for both the rows and the columns, and then we fill in a cell if there's an edge between them. And importantly, what we've also done is sort or permute the different rows and columns of this matrix to try and reveal patterns. So here we've used a technique called seriation, which tries to put closely related actors near each other in the matrix, thus hoping to reveal clusters along the diagonal here. And so already we can actually start to see interesting substructures that were missing from the other diagram, though perhaps with some additional training required to be able to read this particular view. And so, for example, in this giant center blob, what we're actually seeing is subdivision within what was before that giant hairball. And in fact, there's actually 3 different subgroups that actually correspond to different research communities and also different departments at UC Berkeley where I did my PhD studies. So here, by interactively moving through different representations, we can start to build different insights and perspectives into our data. However, even more caution is still warranted. So what I've done here is jump into a visualization technique and then also apply statistical methods, in this case seriation, to try and sort the data into a more useful view. But I would always caution you to also look at the data in some sense in its rawest form. So for example, let's take this matrix, but just sort it by the IDs of the people on Facebook. So here all we've done is sort the row and columns by Facebook ID, which if you're familiar is something like a counter. It basically tells you when people join the service. So now what do we see? Well, what immediately jumps out to you is this big empty white square in the bottom right of the view. And if we were to take this data at face value, what it would tell us is that newcomers to Facebook don't friend each other at all. And if you've spent any time on Facebook, you probably have a good intuition that this is probably false. So what's going on here? Well, in fact, this is actually a data quality problem, and that I tried to be clever, get all my data from Facebook in a single query, not realizing that it silently fails with a 5,000 limit on the results. And this was not revealed to me until I actually thought about creating the right set of views and exploring the data and exercising skepticism. Otherwise, I might have just run with those other views, then gone on to apply any number of analytic algorithms that would have given me inaccurate results because I didn't properly diagnose what's going on in my data. And so this is trying to help illustrate why it's so important to combine different techniques, statistics, visualization, interactivity, and human judgment to really get the most out of data sets. And so while obviously I care a lot about visualization, what I care about more is the overall process of data analysis, which includes everything from how we find, clean, and integrate data, how we explore it, how we create models, and how we communicate results to others. And while it might be convenient to think about this process as a sort of a waterfall as we move from one stage to the next, just a small amount of observation will convince you that in reality this process looks much more like this. And we're constantly iterating through different phases, so a visualization may unleash new data quality issues that we have to address, et cetera. People actually move iteratively as they sort of bootstrap their understanding and their hypotheses of what's going on within a data set. And so what I'd like to do in the remainder of this talk is just give you some examples of projects where we're trying to identify bottlenecks in this overall life cycle of analysis and generate new interfaces to help people work with data. So let's start on the topic of visualization. So one motivating question for our group is, how can we support expressive and effective visualization designs? That is, how can we create visual representations of data that really help us get insight? And it turns out this question has a long and rich history spanning centuries, if not more. So let's look at some examples. So this is maybe like the first economic dashboard ever created. This was created by the Scotsman William Playfair, who among other things was the inventor of the pie chart, which actually only has a 200-year history. And what you're seeing is a mashup, a visualization of economic indicators, so the prices of wheat and then the wages of a good mechanic. I don't know how they figured out what was good, but we'll take their word for it. And along the top, we see the reigning monarchs. So we know who to blame if we don't like the economic situation at the time. So this is, again, over 200 years old, where really people started to collect data and begin to create representations to better understand it. Here's another classic example. This is by the nurse Florence Nightingale, who was concerned about the hygienic conditions in the English army in the Crimean War. So here you see a somewhat exotic time series, basically shown as a radial plot. And the red areas represent deaths due to battlefield injury. Black represents deaths due to other causes, and blue represents deaths due to preventable diseases. So when you see like the primary killer of the English army was bad hygiene, and you might wonder, well, why this exotic visualization? Why not just use a standard time series or table? And to this, Florence responded that she wanted to affect through the eyes what we failed to convey to the public through their word-proof ears. So in this case, trying to use graphics as a rhetorical device. And of course, no survey of visualizations will be complete without including what Edward Tufte has called perhaps the greatest statistical graphic ever made. This is Menard's depiction of Napoleon's ill-fated march on Moscow. As you can see, his army advanced from Central Europe into Moscow, then get decimated, particularly upon their return as they're treated to sub-zero temperatures as shown in the graph along the bottom here. So these are some classic examples of using graphics to try and bring order and better communicate data. And let's look at some more modern examples as well. So here's a simple time series, but we can also couple this with interaction techniques. So for example, I can take this zoomed out view along the bottom and then interactively drag to find focus regions to explore the data in greater depth. I can then look at multiple dimensions. Here's a particular technique called a scatter plot matrix, where we look at all pairwise combinations of variables to be able to look for higher order issues in the data. And again, we can couple this with interaction techniques. In this case, I'll use a method called brushing and linking. By dragging out a region in one chart, I can see how all the corresponding data points project across all the other dimensions in my data set. So for example, if I identify a cluster within one bivariate view, I can see how that holds up across other dimensions in my data set. In this case, we try and engage in multivariate reasoning by looking at all pairwise plots. Other techniques try and take multiple dimensions simultaneously. Here's maybe initially perhaps intimidating technique, but one that ultimately can be quite useful, called parallel coordinates. And what we've done here is visualize 7 different dimensions of a data set and plotted each one as an independent axis. And then for each row in our database, we just connect up all the points along the axes as lines. So for example, I can now look at this chart and then interact with it to ask questions about the full data set of cars. So I might drag out a region indicating all the cars that are heavy, high in weight. I see that uniformly they tend to have good acceleration. That is, their time of 0 to 60 miles per hour is quite low. But they also have atrocious mileage, as shown in the axis second to the right here. And by dragging around, I can actually explore and query different regions of the data. And by querying multiple axes, actually engage in multivariate exploration and reasoning, all in a graphical form. In this case, exploring, again, 7 dimensions of data simultaneously. Now, all of these examples I've shown so far really are what we call tabular data, things that might fit well in a spreadsheet. There are, of course, other types of data as well, including cartography and networks. This particular example shows airports in the United States sized by their traffic. And as we mouse around, we can see all the different connecting flights that an airport provides. And what you might notice is that I near a point, it selects, even without me mousing over it. And so there's actually a secret visualization at play here to support interactivity, in that underneath the hood, I've created a Voronoi diagram so that as I enter a cell, the nearest airport is automatically selected to make the whole visualization that much more usable. Other types of data we care about are other forms of networks. In this case, we're visualizing dependencies among modules in a large software project. So each text label on the periphery here is a particular source file, and then they're grouped by the directory structure of this particular project. And in the center, we have edges connecting files if they have a dependency between them. So I can mouse over and for each class, see how it depends or imports other classes within the project. And this way might help me become a better software engineer. And I'd point out that if I were to draw these edges naively, I get a relatively uninterpretable mess. And so here what we've done is actually take spline curves as connections and then route them according to the underlying package hierarchy of the software. And by doing so, we can see both individual connections, but also bundles, seeing how different sub-packages depend upon each other, thus getting a sense of coupling within our software architecture. And of course, there are many other concerns we care about in visualization, including interactivity as well as animation. So here's just a set of a variety of the types of animations showing the different types of representations we might consider, even for a very simple set of time series data. And while I wouldn't necessarily recommend all of these different views for your data, it does give you a sense of sort of the richness and the large decision space available to us when we start thinking seriously about data visualization. So it turns out actually all of these examples I've shown you were built using a framework we developed in our research called D3.js, or data-driven documents. This is actually a declarative language, it's a domain-specific language written in JavaScript and runs in the web browser to allow you to create rich interactive data graphics of your own. So if you're interested in more, this is actually an open source project. You can find it on GitHub. Where currently it's the 6th most popular project on the world's most popular open source sharing site. And some of you may have heard of this already, but for those of you who haven't, you've probably used it, but perhaps not known it. So for example, a couple months ago when we had the election, the New York Times published a number of really rich graphics allowing us to understand the dynamics of the election. In this case, including all the different paths Romney or Obama could take to potentially win the White House. And this graphic was itself created with data-driven documents, or D3. For those of you who are music fans, actually, this is an image from the MTV European Music Video Awards, where all the displays were done by our friends at Stamen Design. And indeed, all of these different displays showing real-time Twitter traffic around different music stars were also implemented using D3. And so this is really fun for us as we set out to build tools for engineers and scientists and inadvertently provided the infrastructure for Lady Gaga's Twitter tracker. So those are some of the issues we care about in visualization. But all the examples I've shown you so far actually only involve maybe dozens to hundreds, maybe at the upper limit, thousands of data points. And I know many of you at your companies and others in science are dealing with much, much larger data volumes than that. So some of the other research questions we care about is scale. So for example, as a challenge question, how can we visualize and interact with billion record databases in real time? And the short answer is we typically have to find some way to reduce or summarize our data to then make it palatable both for the computational techniques, but also for human perception. So here's one example. This is actually visualizing a 4 million element data set of check-ins on BrightKite, which is a location-based social networking service. And here we've taken those 4 million data points and loaded them into a state-of-the-art system, Google Fusion Tables. To deal with scale, this particular system, Fusion Table, uses a relatively clever stratified sampling algorithm to try and select data points to show you in a way that helps minimize clutter while also maintaining some representativeness. And while this is useful, I would argue that this particular visualization doesn't teach us much other than that unsurprisingly, most people tend to congregate in cities. Now compare that to a different approach where instead we create a heat map. In this case, we bin the geography and then estimate density by counting up all the points within each bin. So using this binned aggregation, we can actually get a better summary of the entirety of the data. And in this case, many different features that we couldn't see before are now apparent. So that might include, for example, people checking in on the interstate highway systems, the existence of Mexicans and Canadians. And on top of that, you might have noticed an interesting pattern down in the bottom right where you see this trail, and that's not a user on a cruise. That turns out that one user created an account to track the progress of Hurricane Ike. And so these are all the types of surprises that typically lie in wait when we work with real-world data. And we want to see the overall patterns and structures, but we also want to be able to be sensitive to outliers like this that may tell an interesting story or actually may be in need of data cleaning. We don't know. And in addition to these scalable representations, the real challenge comes in making them interactive. If I'm going to summarize millions to billions of data points, how can I still engage in this rich interactive exploration? So for example, I might want to couple my map view with a number of other views, in this case showing different time levels, so month, day, and hour histograms. And then I'd like to be able to interact between these different charts using these brushing and linking techniques to in real time be able to explore subsets of the data and refine and develop hypotheses of my own. And to support this, we built a system called Immense for immense data, which supports real-time visual querying of very large data sets. And so underlying this challenge is the fact that we're dealing with a potentially huge space of bins. Remember, we're binning the data to be able to aggregate and show these patterns. And even with this simple example of 5 dimensions, if we look at the entire possible space of bins, it's actually 2.3 billion possible elements. And with small data, this is rarely a problem because most of these bins are empty, and so we can use sparse representations. But as data get large, we also we actually lose sparsity. We get much more density, and we deal with this challenge. And then we have to run queries over this data set in order to support this interactive brushing and linking. So what can we do? Well, we actually took inspiration from existing systems like Google Maps, which provides a seamless experience of navigating around the world, but doing so actually using a discrete set of different tiles by which you stitch together all the imagery of the world. So we had a similar idea, but rather than deal with images, how can we do this with data? And how can we do this with multiple dimensions of data? And this led us to a notion we call multivariate data tiles. So the basic ideas was start with our large, full data cube, but then we can decompose it into a number of projections. So for example, if I only want to visualize a map with a particular time variable, I actually only need 3 dimensions of data, so I can sum over all the other dimensions that I don't need for that view. And I can do this for a number of different dimensions, and then actually use these subsets of data to support interactivity and visualization. And we have a nice feature here, which is that we don't get an exponential explosion because we really only need a maximum number of 4-dimensional projections. And the reason why is that if we're dealing with 1D or 2D plots, we have a natural limit on the number of dimensions that we're comparing at any one time. So for example, if I had 2 different scatter plots with disjoint data values, I need a total of 4 dimensions to be able to do all the querying amongst those different dimensions. But now furthermore, I may still have some projections that are too large. So for example, if I'm dealing with a map, I might have many, many bins to cover the Earth. So of course, I can also segment by index range to develop smaller tiles as well. And it turns out this has some nice effects. I've gone from 2.3 billion bins down to a much more manageable 17 million bins. And for reasons I'll show shortly, we can actually get this really small down to just 350K of data that we can send into your browser to support exploration of this multi-million element data set. So what we do is then decompose these data. It turns out for this BrightKite example, we only need 13 data tiles. And here's why. One data tile we need is for the upper quadrant of the map, plus 1 time variable. So this is one 3D subset of data that allows us to do linking between these 2 different regions of a chart. And then we can repeat this for the other histograms, and then across all the other areas of the map. So that's 12. And then for 13, we have one 3D data cube for the 3 histograms themselves. So what we've done is created this piecemeal reconstruction of our data set, which supports all the interactive operations that we need. So finally, we have all this data, and we can actually fluidly load this into the web browser to support interaction, including panning and zooming. But we still have to compute queries really quickly on the fly. And so for this, we actually use a technology called WebGL, which allows us to move all the computation to the GPU. So we actually just use a 2-phase approach where we take our data tiles, bind them as images, we pack the data into image textures, and then we can run both querying and rendering in parallel on the GPU, which allows us to make this interaction incredibly fast. And so, for example, in benchmarks, a full data cube is not only slower, but actually fails because we run out of memory once we get beyond 1 million points, whereas our system allows us to have 50 frames per second interaction with billion-element databases. And you'll see that by preparing these data into tiles, we actually are able to have constant performance despite the underlying original data set getting larger and larger and larger. So in this way, we can start to explore more interesting systems approaches that allow us to maintain the benefits of interaction and visualization as our data scales. And so, of course, these are just examples of doing exploration with data around visualization, really at the phase of what I call exploratory data analysis, you know, a theme first proposed by the statistician John Tukey. But of course, data analysis involves much more. And so I want to leave you with one final example, talking about how some earlier and very painful parts of the process, in particular data cleaning, can also be supported through interactive techniques. So here's a quote that came from a series of interviews we ran where we tried to figure out what are the real problems in analysis today. And we heard many, many analysts say something like this, that more than half of my time is spent integrating, cleansing, and transforming data without doing actual analysis. Most of the time, I'm lucky if I get to do any analysis at all. And in fact, actually, we got a rough estimate about 80% of the time of data scientists is actually spent on munging data as opposed to gaining actionable insights. And so we see this as something of the elephant in the room of data science work and data analysis research. This is something that we're spending all our time doing, yet perhaps not talking enough about and trying to address that core problem. And this happens even with relatively well-structured data. So for example, here's your tax dollars at work. This is data directly from the government, the Bureau of Justice Statistics. Here looking at housing crime data across different years in different states. And while easily readable for us, go ahead and try and load this into Tableau or R or any of your common database packages and it will break. And instead, people are doing hours of manual adjustment in Excel or writing one-off scripts in Python or other scripting languages to transform their data prior to analysis. Well, can we make this into a more fluid and interactive process was a question we sought to address through a system we built called Data Wrangler. And let me show you how this works in practice. So here we go. We'll load some data into Wrangler. Again, it's a simplified version of the housing crime data I just showed you. So we click Wrangle, and we load the data into our tool. And here we see a data table here in the center. And off to the left, we see a script of operations. And already 2 actions were taken on our behalf for this data. We basically split the data into rows and columns because we saw new lines and we saw a repeating pattern with commas. So we went ahead and took those actions that we could undo them if we wanted to. And now what we'd like to do is take this data and transform it into a new format that we can use with our downstream analysis tools. So one thing we want to do is get rid of unnecessary empty rows. So in this case, I'll just click row 2 because I see it and I would like to get rid of it. And on the left, you see I get suggestions of possible operations. One is to just go ahead and delete row 2, which is the row I selected. But I hit the down arrow and pick the next suggestion, which says delete all empty rows. So our system actually analyzed the data, saw that it was empty, and so created a more general suggestion for us in this case. And then you can see that in red, we've actually visualized what the effect of this transformation will be. So I can go ahead and hit enter and delete all the empty rows. Now I'd like to do something a bit more complicated, which is associate these state names with the rest of the data in my table. So to indicate my interest, I can go ahead and select the text Alabama, and the system correctly infers that I'm trying to do an extraction. But it gets it wrong. It makes a simpler guess and thinks I'm just trying to extract based on indexes into my string. So I could read through the suggestions, or I could just go ahead and start giving more examples so that the system can update its inference. So by selecting Alaska, I see now that I'm getting much more correct inferences. If I check in the transform suggestions, I see I have basically learned a regular expression to extract the word after the text in, which for this data set works perfectly. So now I can go ahead and hit enter, and I've extracted out the state names into their own column. And as I'm doing this, you may have noticed some other aspects of this particular view. So for example, with each column, there's little indicators showing the best guess at a data type. So Wrangler thinks that this column is numeric, and it thinks this column is a string. And then it also has these colored bar charts. In this case, green is indicating the proportion of data values that match the current data type, and red is those that don't match. Similarly, over here in the next column, the gray region indicates all the missing values, as we have lots of empty cells within this column. So I actually can go ahead and click this and get suggestions for how to deal with that type of data. So what might I do with missing data? Well, one thing is to delete them, but the next suggestion is to interpolate. So in this case, I can just copy those values down, and this fills out the table in the way I want. And now we're getting much better formatted data, but now I want to get rid of those extraneous rows that I no longer need where the state names originally came from. And to do that, I could just delete the data that doesn't parse, or I could delete data that is empty in another column. But those might be brittle. Maybe there's data that doesn't parse, but I'd actually like to fix because there was an entry error. So to make sure I get a good deletion rule, I'll go ahead and select the text reported crime in, because I would like to delete the rows that have that text in it. And at first, the system thinks I'm trying to do an extraction, and it's wrong. But I can subtly give it a hint and tell it what I'd really like to do is look at deletion possibilities. So once I do that, it now updates the inference, kind of constrains its search, and suggests to me exactly what I want. Delete all the rows that start with the text reported crime in. So I can read that in the suggestions, and I can see that visualized. Great. So I go ahead and hit enter. I execute the transform, and now I actually have a data set that I could load into my other tools. So how do I get it out of here, out of this tool? Well, I go ahead and click export. In this case, I have a small data set, so I can just go ahead and export it in any number of formats, so column-separated values, JavaScript object notation, et cetera. But imagine my data is much larger than something I could fit in a browser-based app. Well, instead, I could take a subsample of that data, pull it into this tool, and interact with it. In doing so, I'm actually building up a series of operations. And what you're seeing in the history here is not just a plain text description. This is actually a rendering of commands in our own programming language. So all that interaction, what we've actually done is create a program that transforms our data for us. So I can actually ask the tool to export a script. So now it provides me the Python code that implements the transformations that I just demonstrated. And similarly, I could export things such as JavaScript to run on the server in Node.js, or other things like creating SQL queries I can run in Postgres. In the lab, we've also exported MapReduce programs that will transform large data sets at scale. So again, we're using interactivity and visualization to make it easy to author transformations that we can then run on large scalable infrastructures. And so that's just one notion of a system that we can do to help accelerate people's work with data. And so we've since taken this work on Data Wrangler, which is free online if you want to play with it, but also begun to commercialize it. So we've actually founded a startup named Trifacta based down in San Francisco. And so again, that's an example of really taking this philosophy of interaction and applying it to other tasks in the data lifecycle, such as cleaning. And so in this short talk, I hope I've convinced you that there are a number of really interesting both industrial and research challenges that lie throughout the lifecycle of data. And by thinking about how we can take not just scalable processing and smart machine learning and statistics, but really make them actionable through the design of interactive interfaces and appropriate visualization techniques, we believe we can fundamentally improve the state of the art and how people effectively work with data.